Hi, I'm Andreas Olofsson. I'm going to be presenting here today on work we've done on simulating million core systems with Switchboard. And I'm standing in for Stephen Herbst, who's the main architect and author of this work. But it's been a joint effort over 2.5 years now. The other co-authors are Moroze and Edgar Iglesias. So the motivation for this work was to simulate chiplets. So when we started Zero ASIC in 2020, we were going to create a system of composable chiplets, a very large library of size M, and then a breadboard-like system with N sockets on it. So that's a very, very large verification and validation space. So how do you know that you actually build what you should have built, right? So did you build the right thing? And then once you build it, did you actually build the spec? So did you need to verify it? So the size of that verification space places great demands on the simulation infrastructure. So when you look at simulation emulation, you get multiple customers or use cases. So the first one being software. So the people writing software models and firmware, you need to give them something to run that software on, or otherwise they're going to have to wait until the hardware comes back, and that's way too late. So you need to give them emulation model for that. So these are things like QEMU, or maybe large and fairly expensive emulation boxes that run on FPGAs. Second one is, did you get the performance right? And so even if you're functionally correct, you could build a useless device. So you need to know that it's performant. So in things like memory bandwidth, IO bandwidth, balance, and so forth. So sometimes people use Gem 5 or System C for things like this. And then finally, before you push that $1 billion or $100 million tape out button, you need to make sure that everything works correctly. All your synchronizers, your FIFOs, your weird lockups, deadlocks, and things like that. Do you have any of those in your system? And then usually you buy a very, very expensive emulation machine and you make sure the chip you tape out runs on that. And these things have fairly different goals. So when you're running cycler accurate emulation, of course, you'd like to run it as fast as possible, but that's very difficult and very expensive. And when you're doing software development, you mostly care about speed. You want to run this thing at hundreds of megahertz because you want to go through quick iteration cycles. And so if you can't have the best of both worlds, you need to make some trade-offs. And usually the trade-off is to make coarse models and slow and expensive RTL simulation, but you don't have both. So this kind of sets the framework of the area that we're working in. And before we started this work, we looked at what was out there. And of course, there are the commercial emulators, which are expensive. And because they tend to have a requirement that they have to run Verilog code out of the box, they tend to be fairly slow, on the order of megahertz, single-digit megahertz to run. Something that's faster would be the FireSim out of Berkeley. And that's a very extensive system for mostly CPU-centric emulation, or at least it started out that way. And so when we looked at this platform, we decided that we need to go on our own path for chiplets. There were certain things that drove us in that direction, specifically flexibility and our focus on very, very small devices and many, many of them. So that kind of sets the stage. And then when we started working on this thing, we had some principles that we laid out. The first thing was we are going to lean into latency and sensitive interfaces. It's something I used at Adaptiva 15 years ago, something that people have used successfully for decades. It's the correct thing to do correct by construction design, and it scales extremely well. So we wanted to build a platform that scaled and that was composable. So it seemed like the right thing to bet on. And then the second one is multi-abstraction standardization. And that means there's not going to be one perfect abstraction. So we need multiple levels of abstraction for different fidelities and speed. And so we figured we're going to build that into the framework from day one with the proper standardization and proper interfaces. And the third decision we made was that we're not going to go for 100% accuracy. And so getting to 100% accuracy is exponentially more expensive as you try to reach the 100%. And that doesn't matter if you're talking about cycle accuracy for verification or peak performance. And so we decided, because of our small team, we're not going to go for that. Instead, we're going to go for a bounded validation. So something that tests out cycle accuracy on certain partitions, but not across the whole system globally. And for performance, If we're within 5-10%, good enough. We don't need to be perfect. And then the final shortcut that we took, we are going to impose, if you want to scale with the system, we're going to impose explicit channels between those partitions. So we're not going to try for the really, really hard problem of auto-partitioning or auto-parallelization across a cloud scale computing framework. So those are kind of the decisions we made. And so the framework that came out of this that Stephen really invented and pioneered was the switchboard. And so it's at the core of it, it's based on a shared memory queue implementation with latency and sensitive interfaces. And this was open sourced in October 2023 together with our public emulation platform and is available as a Python package from PyPy. And so far, we've demonstrated RTL simulations, FPGA emulation in F1, and Python, as well as C++ and SPICE models, all working with this within this framework. And if you want to get a deeper dive into the theoretical underpinnings and everything else around this framework, you can look at our archive paper. There is some information in this paper, but because of the page limit, we put the rest of it in this archive paper. So now looking at some of the details of the switchboard framework, at the core, as I mentioned, we have this latency insensitive channel. So this is a static connection. It's unidirectional, single producer, single consumer, and it's latency insensitive, right? So there's, in one sense, not a lot to see here, but this is a very robust implementation. And we have a fixed packet format that we stuff all these things into. So this is an example of the power of standardization when you pick the right standard. So if we look at how this is implemented in different levels of abstraction or different domains. So the first one, you look at RTL, we can implement this switchboard connection using a valid ready interface, like something you would see in AXI or in our Universal Memory Interface, UMI. We have the same thing, and it checks all the boxes. The one addition here being the addition of clock. So this is our universal timekeeper. So when you're doing hardware, you do have to kind of decide if you're going to be an asynchronous design or if you're going to be a clock synchronous design. And in our case, we do all of our implementation with rising edge clocks and synchronous design. So if we go into the next level abstraction, we can also implement these switchboard connections in software using queues. And it turns out that shared memory queues are very, very fast on modern machines. And so we're talking microsecond type latencies to interact with these queues. And so the idea is that you write data into the queue from a transmitter of the switchboard connection, and then you pick up elements from this queue from the receiver. And then the queue is also responsible for doing ready valid handshakes between the two blocks, the receiver and the transmitter. But in terms of treating transactions in and out of these shared memory queues, from the outside, it looks like a fixed unidirectional single producer, single consumer, latency insensitive channel. Now, when we want to hook up the RTL simulation with the ready valid to software with the queue, we need an interface. And so in this case, the solution is the RTL we run in a Verilog simulator like Verilator or Icarus. And then we need some way of reaching into the C domain with the shared memory queues. And you can choose between DPI or VPI. Generally, that may depend on the simulator you're using, which one they support, what your preference is, but you do need that adapter. And so the added complexity in Switchboard is simply by creating this adapter framework. So using these channels, we have implemented RX and TX, right? So both sides of the channel in RTL, FPGA emulation, in AWS F1, C++ models, as well as Python models. So there's a lot of universality here, and I think it really speaks to the strength of the implementation and the framework that we've been able to pull this off with a very small team. So now, if we go into a small example, how would you use Switchboard to go from Python code to drive an RTL simulation in something like Verilator. And so this is showing, writing data into a piece of RTL code, in the RTL code, adding 1 to that value, and then sending the data back to the Python world for inspection. And you can find this example up on the Swtichboard examples tree. So in order to do this, we need some glue code, of course. We need some way of telling the RTL simulation how to interact with the software world. And so in this case, we need to include a header file into the Verilog code and into the test bench of the Verilog code. And then we need to instantiate these queues. And so these are named queues. And this is really how these named file queues is how we make the connection between the RTL and the simulation. And then in the middle here, we see where the code actually would go, the instantiation of the hardware model. On the Python side, it's besides being a fairly traditional Python environment, Python program, we do need to instantiate this device under test, this switchboard dot, and also call in the system Verilog file for enumeration or elaboration, and then instantiate again the queues that we named in the RTL code. And then we use these send and receive main calls, right? This is how the main communication happens, to communicate back and forth. So the pattern here that is very, very familiar is send and receive and establish static channels between two devices. If we're not happy with the Python speed, we also have a C++ interface that looks very, very similar. Instead of the Python code, we got our main code. We instantiate the connections. We initialize the files, right? The read and write queues, and we instantiate the DUT, the device under test. So now getting to the bulk of this paper, how do we do massive simulation? So the inspiration for this work was we started looking at wafer scale processors and the need for simulation for those processors. And these are a massive processors that couldn't possibly be simulated or emulated in a single thread. They can't even fit on the most expensive emulation machines in the world today as a single unit. And we're talking about millions of cores, or at least 1 million core from Cerebras and Tesla. And personally, I think this is going to be an area that's going to see a lot of innovation in the next few years. Scaling is winding down, and if you can't scale down, well, you scale out and up, right? That's the next Moore's law, and so that's a prediction we're making here. So the main idea, how did we get here? And this is an idea from back from 2011, actually, that I had, but I did not have somebody like Steven to implement it. Nor did we have the switchboard framework built up. But the idea is that if you have a regular topology with a finite number of unique hardware blocks, we can pre-compile those blocks. And then with the correct interfaces, like a latency and sensitive interface, we can actually just wire them up together without having to compile something. So that makes things very, very quickly. And it scales very well when you start repeating blocks. And that works at the silicon compilation level as well as at the simulation level. And that's really the main idea here, is that we have a finite set of pre-compiled blocks that we can then stitch or wire together very, very quickly using these shared memory queues. So looking at a baseline, couldn't we do this in Verilator? Verilator was not built to compile to cloud scale. It's built for multi-threaded shared memory machines, and so we ran some experiments to start off with, and quickly see that both the build times and the simulation times are not going to get to 1 million cores. This is showing values for up to 8,000 cores, and we see that for build time we're already at 2,000 seconds for 8,000 cores, and then we have over 100x to go after that. And I think it's fair to say that nobody wants to wait for days to compile a Verilog design. That is unacceptable. So there was definitely a gap here that we tried to address. And so the architecture, right, the optimization we did to pack these simulations into AWS, which was our fabric that we simulated on, was we packed 10 times 25 CPU grid based on PQRV32s into to one unit. That was one simulation task. And then we'd pack 16 of those simulations into a machine, because that sort of would fit with 16 virtual CPUs and 32 gigabits of RAM. And then we'd just scale that out across a cluster. And so, and just to have something to run, we ran a matrix multiplication workload, right? The kind of thing that you would see a lot of in AI, and a systolic array specifically. And this is not an optimized implementation at all, but it's always really, really nice to see a result come out. It's really, really rewarding instead of just running an arbitrary experiment. So this is, again, systolic array. You have, each CPU is computing and storing one element of B, and or storing one element of B, computing a MAC, and then you're shifting in the A matrix, the A values, and then and the results get shifted down southbound. So the results. Running through this million core simulation, we took the Pico RV32. The default values we set to 1 are multiply, divide, RQs, and trace. So it's a fairly small version of the Pico RV32. And compilation times for a grid of these, or tile of these 10 by 25, is at 3 minutes and 26 seconds, which is fast enough, I would say. We upload that image to AWS, and then we launch these tasks. And you can see the breakdown here on the left side. It takes about 10 minutes to run through, and part of that is just launching this massive network of tasks, and then waiting for it to boot, and then finally actually running the program, running the simulation. And so you get to the main result, which is you can get from RTL change to running a million core simulation on a decently large benchmark, right? In this case, it's a billion max for 1,000 by 1,000 multiplication of matrices, and all of this is under $41 and 15 minutes. So I think this is a pretty good result. So to summarize the work here, Swtichboard is a high-performance open source framework for wiring up a mixture of hardware models. And we have two results here. One, we have build times that scale as about 1,000x faster than multi-threaded validator on a million core design. And we have about a 20x speed up or 19x speed up compared to an extrapolation of this multi-threaded simulation, because we couldn't actually compile a million cores on Verilator. But we're definitely very encouraged by these results, and we are doubling down on this development going forward. So if you have any questions, let me know. Contact me or contact Steven directly, or go visit the Swtichboard repo and try it out. All right. Thank you.